at the 2021. Now, before we look back 2021, it's basically how we see the field has been developing is looking even before 2021. So I want to first take a look at the years, I would say 4 years before 2021, from 2017 to 2020. The reason I picked those segments is during that 4 years, there is a revolution going on. So the whole deep learning field basically started from 2012, where the ImageNet got surpassed all the other computer vision model to demonstrate the deep learning convolutional neural network has a high, much better performance than the classical machine learning method. So from 2012 to 2016, that is the takeoff of computer vision with CNN. Since 2017, the transformer was invented, and from there, the whole field of NLP, natural language processing, has changed. So basically that year, actually this is better to show you the transformer development in the last 4 years. So the major development for NLP domain is the invention of BERT, which is training the transformer on a large language corpus that's called a pre-trained language model. With that, that can basically solve all the classical NLP problems. Next year, GPT-2, P5, BART, or all these more sophisticated pre-trained model appeared. In 2020, GPT-3 was released. So as you can see, the whole NLP field by the time of GPT-3, it's become very pretty much solved. The classical NLP problems are solved, whether it's a text classification, sentiment analysis, the parsing, semantic understanding, name entity recognition, all of those classical NLP problems are pretty much solved. In the same time, the computer vision also surpassed the human performance in all the image recognition, in object detection, video tracking, image generation. And all those data was achieved before 2020 with convolutional neural network. So both fields has made a big progress even before 2021, before last year. In the meantime, reinforcement learning has also made a lot of progress. Basically, through deep reinforcement learning, they are being applied to robotics, to medical domain, to autonomous driving. So by end of 2020, the field itself has come a long way, and the deep learning become the dominating method. However, inside the deep learning, we still have two major paradigms. One is transformer-based for natural language processing, another is CNN for computer vision. And the reinforcement learning basically is sometimes mostly use CNN, occasionally they use RNN, and even start to use transformer. So that is the field at the end of 2020. Now, what happened in 2021, just last year? What we are seeing is a complete takeover by transformer in computer vision field. So I'm going to show you some actual results that how transformer surpasses CNN in computer vision. In the natural language processing, we have basic classical NLP problems are pretty much solved, but there are a few remaining very difficult problems. One of them is chatbot. There's also two other remaining problems. One is question answering, text summarization. So we are seeing in 2021, the open domain question answering is being solved. I believe it's a complete solved. It's essentially open domain question answering. We can do very close to the human performance. Actually now, there are only two major tasks remaining. One is the text summarization, another is chatbot. That is the state of art in 2021. In addition, since transformer has been able to represent the image, both image and the text, people unify that in one in the unified architecture, and that allows to do image text processing together. So the not only caption generation, image search, and also image generation based on text. So those the multimodal processing that becomes a reality. The fourth trend as we will see is how we can improve transformer computing itself and also its architecture, because there's such a need for having a faster transformer, have a fewer computing and speed up, not using a huge amount of GPUs. How can we speed that up? So there's a lot of research going on in 2021 in that. In terms of reinforcement learning, we are seeing that it now can apply to natural language processing. They take a reinforcement learning to use that to learn about how to build a web page, the web page design. They use reinforcement learning certainly for robotics, but in a more sophisticated way. So these are the 5 major trends that I want to summarize in this hour. Certainly, there are many other things I didn't touch. For example, the GAN model, the more advanced GAN model. Another thing is the voice processing with the transformer. Now, essentially, transformer also take over the voice speech recognition field. Thirdly is time series analysis. That is also transformer has demonstrated better than other classical models. So essentially, transformer has been sweeping through all the other fields. So I'm just going over some classical, the 2 major fields in the deep learning. But if you know or you want to propose a few other major trends, we can talk about that at the end of this talk. So the first trend that I want to focus is the how transformer change the computer vision field, and it started with a paper at the end of 2020 called the vision transformer. It basically allow us to model picture image now in the way we model language. So when we model language, the sequence of tokens, every word is sent into a transformer, and together with the position encoding, we can process the language sequence. And using that, then we can do translation, we can do the text summarization, all the other NLP tasks. So essentially, transformer is a best way to handle sequence. So the first task is converting a picture into a sequence. So vision transformer allow us to basically take a patch, divide the picture into equal size of patch, and going through them in a sequence in a very orderly way, and remember the sequence position. Using that information, we can do image recognition. So this is the major breakthrough. The vision transformer is the major breakthrough. With the vision transformer, they demonstrated that it surpasses CNN in several tasks. So if it's trained on the large Google internal image data set called the JFT, it achieved 88.5% in ImageNet, which has not done before, right? So if the biggest ResNet achieved 87%, but the vision transformer achieved 88%. And the same thing goes with all the other image data set. So this is a big news for the field. From there, the researchers continue to refine vision transformer. For example, from Facebook, the so-called data efficient image transformer, they use a vision transformer as a backbone, but they added a data augmentation to train the classifier. And since they don't have the JFT, the Google internal data set, they only use the public ImageNet data set to train, but they can augment the data by transforming the data in many, many ways. So, and adding some distilled model from the original best image model, they can achieve 83.9%. So that is That is a kind of state of art for the basically self-training in the transformer, vision transformer. Then people take a vision transformer forward to process a video. In order to so if you think about a video, what is a video? Video is a sequence of image. So in this case, so basically you mentioned multi-scale vision transformer allow us to do both image and multiple video frame. And the way they do that, they first chunk them into small patches or small cube if it's a multiple image in the video. Then they process the smaller cube into larger cube, so then summarize that information. Then they build through transformer, they build a network so they can sample low frames or high frame rate, depending on how many samples you want to achieve, and then concatenate them into the vector to be processed later. So they call it slow, fast network. And for them, they tested on the video data set with one, it's called a kinetics data set with 400 action class, like people shaking hands, riding a bike, playing violin. Those are the actions. So there are 400 action in 10-second video clips. There's another data set with 600 action classes. And you can see that the bottom is the best performance in this video data set, kinetics 400. The multi-scale vision transformer surpassed all the other the previous model, whether it's CNN or the vision transformer itself. So they showed that they can achieve 81%. So this is a very good performance. Then people further developed another video transformer. So this paper is a simplified version than the previous one. Instead of doing all the multi-scale, slow or large sample, they simply use a uniform scale. So with a uniform scale, they take a simple image vision transformer for every picture frame. So it's a very simple way to take the tokens from the image, just the left to right, and then the second row, and then you concatenate them all of them together. This is one way to convert video into tokens. Another way they also experimented is you take a slice over several video frames and take the first token of every video frame together as one token, and then you run through the first batch, and then go to the second batch. So this is a so-called spatial temporal token. With either way, they were able to send that to a transformer. So the transformer inside essentially attended to all these tokens. So the fundamental methodology is a transformer. The only additional work is how you convert the video into the tokens. Inside the video, of course, you also can indicate whether this is a spatial token or this is a time token. Then they can have a different way to attend to spatial token and time token. So there are some additional processing, but fundamentally it's just a big transformer. With this kind of architecture, they showed that with kinetics 400, with large scale pre-training, they pre-trained on JFT, which is the Google internal image dataset. They achieved 84.9% top one accuracy for the video class. And you can see here they compare that to all the previous video classifier that people have developed in the past few years, and this one performs best. So this gives us a very clear evidence that transformer-based video model can be better than CNN-based model. So now we have evidence that the transformer helps both image processing and the video processing. And I didn't show one more paper here. Yeah, I didn't show one more paper here is the applied to object detection. And people show that the transformer also perform better than the classical CNN model in detecting objects. So essentially, as you can see, it's pretty convinced, the field is convinced that the transformer can do as well as the classical CNN model. So I think this year, gradually people started to see the very simple application for transformer for vision, and it's practical now. So given that, the next trend, as I mentioned earlier, is combining the transformer from image with text. So we know transformer can handle text. Now we know it can also handle video. How about we merge these two representation together? So one simple method is if we know some image with captions, we can build a transformer to encode those texts. We can also have an image transformer to encode those images. Since we know they are mapping to each other, we can build this vector. The vector, as long as given them the same size, the same size. So you have the number of tokens from the text, number of tokens from the image, and then you build the corresponding tokens. So in fact, sorry, I take it back. So if you take a batch of image, and then you take so here the n is a number of unique documents. So each document is the sequence of text describing the image, and each image here is just one single image. So you know this whole the first document corresponding to first image. So that's T1 was I1. And so each of them is a vector representation of one is text, one is image. Having this kind of correspondence, it helps us to essentially, so this generator, we can learn directly from this data set without any human label. Essentially, this gives us a labeled data to train the correspondence between image and text. What the result of this training is so-called a zero-shot prediction, meaning if I give you a text, you can immediately retrieve an image for me, and vice versa. So this kind of correspondence help us can train the image retrieval with text without a human involvement. Basically, all it needs is data from the internet with all the captioned image. So this is a very powerful self-training method, self-learning method. And we can see that comparing to classical method, the highest, the red thing is the clip. So this is the method called the clip. Essentially, it's contrastive learning of image and the processing. So contrastive learning of language image pre-training. So CLIP stands for P stands for pre-training. So here, as you can see, there are some pre-training methods. For example, here, SimClear was invented just a year ago. SimClear, 2019. So SimClear was the first contrastive learning that was invented to allow the image processing to learn from generating the different view of the image and train itself. From there, BYOL is also another contrastive learning method to train itself. So all these are contrastive learning, but here we use contrastive learning with the transformer architecture, and also combining text and image. So this is the innovation, and it shows that perform much better. As you can see, the ResNet, if you use ResNet as a backbone, it's below the solid line, right? So that is a very interesting performance. Now, taking this further, how can we do the text to image generation? So we can do text to image retrieval. That's what the clip did. We know they're corresponding. We search for the internet, and we can find the text or find the image corresponding to the text. But what if we can actually actually generate pictures by computer by itself? So here's what OpenAI has done. It's a very interesting image generation method. This whole method is also connected with the transformer. So this is the illustration of the ending result. If you give the computer a sentence, a text describing there is a baby hedgehog in a Christmas sweater walking a dog. So you have several objects here. You have a baby hedgehog, you have a Christmas sweater, you have a dog. All of this will come into this image, right? The computer can, all these are drawn by the computer itself. It's not, it didn't exist on the internet. Then you change the word sweater into a t-shirt. So it will show you then a hedgehog in a Christmas t-shirt. And you can say walking a cat or walking a chicken, walking a sheep. All those words can be replaced by a different object, and then the computer will draw a different picture. Same thing here. We were playing with different shape, right? You can say a shape of strawberry. If you change that to a shape of avocado or armchair, it will draw all the green avocado chair for you. So this is very powerful. And the same here, it show that if you just change the text to it's the same text except the one word was replaced. Say, so the first word is a painting of a fox sitting in the field at a dawn. All those words can be replaced. Whether it's a fox, it's a wolf, it's a tiger, it's a, you can change it, right? And it either can be field, can be dawn, can be sunrise, sunset, on the moonlight. The field can be replaced by forest, mountain, all different words, and you can draw different pictures. So that's you can play. Actually, this is on OpenAI website. You can play with that, and then you can also change the style of painting to different style, to certain artist style. Van Gogh, Monet. You can change that to pencil. You can change it to a postage stamp, and all these are automatically generated. So this is very amazing result. And how did they actually do it? Essentially, they train a two-stage model. The first is so-called discrete, the variational autoencoder, and this is a generative method that allow you to compress a large image into a small image without losing the fundamental information. And from this smaller image, 32 by 32 image, they then create tokens. They send those tokens to a transformer, which is essentially GPT-3, since OpenAI had the GPT-3, together with the text, the text that you want the computer to draw, right? So for text, they have 266 maximum tokens to represent text. So this concatenated together, they send to the transformer. The transformer has 64 layers, 2 billion parameters, and that is the whole architecture they train. And certainly they have millions examples, right? There on internet you have probably the caption, right? All the captions certainly. So they do take advantage of clip I just mentioned. In the clip, they already pre-trained with the correspondence between text and image. So those model remembers the correspondence, and from there you add image generation. So that's how you are able to draw those beautiful pictures. So this is a big advancement in the processing image and the text, and people are very excited. And just one more thing for the evaluation. So they compare all the image generation based on text. For example, DF-GAN, using a GAN model. All the GAN model based perform much worse than this method. So using human evaluator, they showed that, and they run through some image using the image from COCO dataset, right? Using the caption from COCO dataset, more than 90% times they outperform the DF-GAN in terms of accuracy and the realism. So yeah, so by now we know that transformer did very well for image. Transformer can handle the correspondence between text and image and give us very good image generation. So all this development. The next question is how well does the transformer do in the actually, I was going to talk about the natural language processing. Since yesterday I gave a talk on chatbot, I will touch upon the chatbot after we talk about the transformer improvement itself. So we know transformer itself is a quadratic in the length of the L is the length of tokens. So right, that's why even in this architecture, the length of token is very limited. You have 1,000 image token, 256 text token. The reason for that is the attention, since we do self-attention to every token, is a quadratic in the number of tokens. So the first goal is to reduce the dependency on the length of tokens. How can we reduce the computing, not quadratic in the L in the total length of token, because this becomes a limitation. The limitation will impact several things. For example, if you want to do text summarization on a large document, like a financial report, the financial report can be maybe 10 pages. That how many tokens on 10 pages? Say you have 500 words on each page. That will be 5,000 words to send to the text summarizer. And since today's or classical transformer cannot handle that, we have to use some other ways to change the computing. So sparse transformer was first introduced to reduce this from L squared to L square root L. And if you look at a sparse transformer, the way they reduce the computing essentially is try to take the most relevant, they attend to a limited part of the token that's next to each other, not too far away. So they try to use the local information, so-called the local attention, to give us more like approximation to the actual outcome. However, it is an approximation. It's not a complete. It doesn't give us the real transformer performance. So it's a compromise in a way. Also, the improvement is not that big. So the second improvement. So before I talk about that, let's just talk at why. This basically tells us why it's L squared. So we know that we take three. So based on the input, from the input is a sequence of tokens. From input, we generate a QKV. How do we generate QKV? Is we have a linear matrix L by L. So if you have a L as input, length of input, you have the matrix. You have another length of L in the output. So you have the mapping, the A base maps from the input to the attention before you reach attention token. Once you do that, then you do another transformation to generate the QKV, the query, key, and the value. So those will be used for attention operation. All right, so that's a lot of math. Since I don't have a picture to show you the actual attention, so it's hard to explain how But that give you idea that this is an L square operation. So the reform, another improvement on transformer is called a reformer. Reformer reduced it to log L. So let's take a look at what a reformer did. So I had the performance of so I have a reformer. The third improvement is a performer. So performer actually changed. I didn't show the mathematics. So additional improvement from performer is they actually they are trying to approximate linear complexity. So here in the reformer basically is a reversible transformer. So reversible transformer basically cut down the size of attention and to a fixed size at each layer. So you don't increase your computing as you go forward. And that basically limits the total number of operations. So that's a reformer. But a performer is even better. When they do attention instead of a quadratic operation, they find a way to decompose that into some linear operation between two matrices. So it's essentially factorize the matrix operation. And they showed that it achieved the linear, it's basically O to the L. It's a linear performance. So it's much better than L log L. That's and the experimental results show that the performer comparing to other transformer or under the classical transformer, the black line at the bottom is the speed. So the horizontal is the length of L, and the vertical is the time, how much time it computes given the length go up, and how much more time it requires. So it's pretty much linear in the length of the tokens. And so this actually have a good summary of the speed and the performance trade-off. And you can see performer is on the upper right. It's better than some. It's better than reformer, certainly in terms of both speed and the performance. It's better than linformer and the original linear transformer and the local attention method. Its total performance is not as good as the complete transformer because it still has a compromise. Because when you do matrix decomposition, you still lose a little bit of information there, but not much. Basically, what they're showing here is not too much loss. So that is a trade-off we are facing. So this is an improvement on classical transformer. The idea is that in the future, just with this a little bit of improvement, we can run a very large transformer inside one GPU without requiring many GPUs. And so that is a big improvement for many fields, right? If you want to do a lot of experiment, you cannot afford so many GPUs. Why not just use with a little bit of performance decrease? You can experiment the transformer-based architecture and do many experiments. So that is the goal. And here they show that in 1 second they can process more than 100 data points, 100 examples. Another way to improve transformer is they introduced so-called switch transformer. Switch transformer, the idea is actually very simple. Basically, the idea is that we know the larger the model, the better it performs. So essentially, the total performance, the accuracy is corresponding to the size of the model. So that is given. That is people tested with many models like GPT-3 perform much better than GPT-2. We show later that the BlenderBot 2 with 2.7 billion parameters, the model performs much better than the model with 970 million parameters. So when you double the number of parameters, your performance will increase. That's why we go with a larger and larger model. So So the question is, can we increase the size of the model without increasing the computing? So the switch transformer is trying to solve that problem. So here, how do we increase the size of the model? So they modify the minion. So inside each encoder, you have two layers. One is the self-attention layer, another is the minion, the feed-forward neural network. FFN is a feed-forward network. So in the feed-forward network, essentially it's a linear. It's a simple multi-layer perception. Basically, it's just a node-to-node classical neural network layers. So they divided that into groups. So in the feed-forward layer, you divide all the nodes into multiple groups. So here there are 4 groups from group 1 to group 4. Then they say each time I only use one group instead of all the groups. In this way, each time you don't compute the weights against every tokens, against every node, you only calculate the weights to correspond to a small segment of the nodes, maybe 1/10 of the nodes. That dramatically reduces the total computing. And how can we do that without lose information? Is by using so-called the switch transform the switch. So the switch here essentially is learning about the parameter. You have indicated which group to use, that we call that expert. So one group is one expert, another group is another expert. Essentially, it's a voting. You select the one that give you most likely the high performance, and you can train the network to recognize which expert to use. They also showed that the performance increase with the number of experts, which is not surprising because we do know the number of parameters increase, the performance will go up. So the downgrading, this is the loss function, it's the reverse of the performance. So the loss gets smaller and smaller when you have more expert. And they showed that when they use this against the T5, original T5, the transformer model, they have a 7x speed up, right? So just adding more expert in the linear layer, in the feed-forward layer, you gain much more performance, even though it's the same architecture. So the attention side is the same as T5. Other parameters is same as T5, same number of layers, same number of the embedding size, same number of input size. So all the remaining parameters stay the same, except you add more parameters inside the feed-forward layer, and that give you 7x speed up. So this is a very encouraging result for how we can improve our performance with a better transformer. So this tells us the architecture design of transformer can help us to speed up our performance. It can speed up and also give us a better performance. Now I talk about all the transformer-based improvement. I'm going to talk about the breakthrough inside the NLP domain, which I covered yesterday in another talk. But for those of you who didn't attend that talk, let me just repeat some of the findings. The main finding, what I want to touch upon is the breakthrough in chatbot. As we know that with transformer invention, with pre-trained language model, the open domain chatbot, which is the bot can talk about anything, started to take shape, and they are trained end to end. Basically there's no human involvement. You just train on the text, on what the user says, what the system talks back, and actually no, sorry, I take back. You train on the human conversation. So given the question, you know what the human would say. So you learn from what the human would speak back. Using more than 147 million the data transcription, the conversation from the Reddit. So the dialogue GPT was trained on that, and they achieved relative good performance. Then from there, Mina and the blend bot was designed basically using, one is use T5, another is use BART. Both are transformer, pre-trained transformer. Then in 2021, the big breakthrough is transformer based chatbot, BlendBot 2. So BlendBot 2 used a new architecture called the fusion in decoder, where so the way the open domain chatbot can talk very well back to the user is because they contain a lot of world knowledge. So if you ask who is Steve Jobs, who is Tom Brady, where did he play? So all those questions is factual information. So the bot is able to give you very good answer because they already searched on the internet. They remember those knowledge. In the real time, when they actually answer, they can still do those questions and passage. So somehow they internally not only can give you a interesting phrase, interesting sentence, they also have all the facts, which is sent to the decoder through the kind of question answer retrieval. So this methodology is used for open domain question answering, but then can be later used for the chatbot. So in terms of the breakthrough in open domain question answering, as you can see that the fusion in decoder performs better than T5, GPT-3, all the previous, and it's 10% jump against the previous method, against the GPT-3 and the T5. It's not against a RAG. A RAG is Facebook their own method, so it's an incremental over RAG, but it's still a big improvement, 7%. So this is the architecture that does very well. So that architecture come into the BlendBot 2. BlendBot 2 combines this architecture with two additional capability. One is the long-term memory of the user. So they remember what the user said a month ago or 2 weeks ago. It's when they make a conversation with the user, they retrieve that information from the memory, from the hard disk. So that is one method they use. Another is use a real-time search to answer more updated information on a certain person. And they showed that comparing to other chatbot, they achieved a much better performance, much more human-like. And we know that if you actually chat with BlendBot 2, you will feel that you are really like chat to a real person. It's hard to tell. And the conversation comes back with a lot of empathy, with even sometimes making a joke. They can do a pun. It's just amazing how far the chatbot has become. So this is what I consider is a big breakthrough in chatbot, in open domain chatbot. Now, there are two kinds of chatbot. Also mentioned yesterday that I didn't put the cross domain. Yeah. Anyway, so there is another breakthrough is in the cross domain. Cross domain, not a cross domain. I would say the task-oriented chatbot, where the goal is to accomplish a certain task. So we have come a long way to build end-to-end chatbot to help the user accomplish a task. For example, booking a room in a hotel, or booking a taxi, or booking a ticket, or play a music. All of this, people have demonstrated end-to-end deep learning transformer-based model can actually create a very near human performance in those domains. What's more interesting in 2021 is the implementation of continual learning for those tasks. So this is what I see is kind of a breakthrough. We can allow a conversational bot to remember what it learns in hotel and then carry the knowledge to taxi. In addition, after that, continue to learn to do conversation in a new domain. And the way they achieve that is a simple architecture modification to the transformer. So we know that the transformer has each encoder has two major layers. One is that the bottom is a multi-head attention, and above that is the feed-forward layer, right? Feed-forward network, or you call network because it's two layers. So what they did is add one more layer after the feed-forward layer, and this layer is called adapter. Adapter essentially it's also two layer, a linear layer of two layers, but it's called a bottleneck layer because the internal part of the layer inside the adapter is much smaller than the rest. So you reduce the number of parameters for computing in the adapter. So they inserted adapter into the transformer layer, each transformer encoder or decoder layer. So they added that just right after the feed-forward layer. With this simple modification, then they can fix the pre-trained transformer from the previous domain. So you don't have to change what like the BERT or T5 you trained in the general language model. You don't have to modify, update those weights. All you have to do is learn the new weights for current domain. If you're in hotel domain, you learn about the parameter for hotel. If you are in the taxi domain, you learn another set of linear parameter. So this go on and on. You can just keep adding new domains inside one layer. And this essentially fulfill the hope for continual learning or lifetime learning. So this is a very powerful methodology. They tested on 37 dialogue data sets, and they showed that by adding each domain after one another, so the top green curve, the green line basically shows their performance stays high. And all the other methods, they showed about 8 different methods from previous papers. With other methods, they degrade quickly. So this is a big breakthrough. What I feel in 2021, we will continue. In 2022, there will be continuing research on continual learning, not only in task domain, task-oriented dialogue, it can apply to many other domains. So into robots, to reinforcement learning, to all the other domains. So this is a very powerful result. Now, since we talk about reinforcement learning, I want to come to the major advancement in reinforcement learning last year. So we know that the reinforcement learning has been used for many domains, but it itself still needs a lot of improvement in terms of computing, in terms of building the architecture. So the one improvement is how to evolve reinforcement learning method by itself. So this is more like architecture search or evolve. It's on the line of neural architecture search. How can we define the best reinforcement learning algorithm? Now, what it defines a reinforcement learning algorithm, as we said, reinforcement learning basically has action, state, reward. The major parameter for reinforcement learning is action. What action you are going to take in the environment. And the environment is described as a state. Based on each environment, you get a reward. And the goal is to optimize the total reward, total discounted reward over a time horizon. So that is the goal of an agent. Okay, I didn't copy the result here, but this just give you a flavor of essentially they showed that with this evolved reinforcement learning method, they were able to design different actions. So you have action space. What are the best actions you should choose? And then what is the next step? What you should do? So all those choice parameters can be optimized through evolution, a population of reinforcement learning algorithms. So this is one result. Another result is along the line of model-based reinforcement learning. So we know that classical method is called model-free reinforcement learning, like Q learning, where you don't you don't make any assumption about the world. You just observe the reward, and then you do something. You get a better reward, and then you continue doing that action. If you get a worse reward, you stop doing that action. So and then over time you observe which action give you the total reward over time. So that will be, you continue to learn about that by adding up those reward, and that becomes your Q value. So the Q learning is a model-free learning. There's another camp called the model-based learning, where you actually learn about how the world changes, once you take action, how the world changes to a new state. So using that information, you can predict. It will help you to basically formulate the model about the world. Instead of a random trial, you can use the model itself to figure out what to do next, because you have projection into the future. So this is a so-called model-based learning method. So they use this method to train a robot for walking, right? So I believe here is for in this environment, simulated environment. And so the 2020, this is Dream version 1 was invented before 2021. The invention of 2021 is it's an improvement on the previous model, and the result basically shows that it performs better than the classical deep reinforcement learning method, such as Rainbow. Rainbow is basically a combination of all the improvement on the deep reinforcement learning, including deep Q network and other improvement. So this is a Atari game. So there are 57 Atari games. So they were testing against in the Atari game, and so all of them. So you see the last 3 outperform human gamers. Essentially, so the machine now plays better computer game than humans, which is not surprising after they beat the human in the board game, in the Go game. But Atari is more dynamic game. So now the machine also does much better across the board, not just in one game. So this is the result for model-based learning. There is one more thing I want to show is for applying reinforcement learning to natural language processing. So in the natural language processing, as I mentioned, there are 2 remaining major tasks. One is text summarization, another is chatbot. So chatbot, even though the open domain is very interesting, but still there's something to be tuned there. There is still not exactly as we can control how the machine would say something. So I think the next year with chatbot, we are going to see more controllable parameter to make the chatbot say, make it funny, or make it more knowledgeable, to pretend it more like a teacher, adding personality to the chatbot, or make it. So there are many ways we can change a chatbot. And for task-oriented chatbot, there are also, I believe there should be a better way for annotation, reduce maybe self-learning method to reduce the amount of requirement for training, for labeled data. So that's where chatbot will go, what I predict will go in the next year. Now, with text summarization, it's also very interesting. It's very hard to get labeled data for text summarization. Of course, if you do financial report, you can probably get some human summary. But you look at a financial report every day, there are new financial analysts write articles about certain companies. There are not many people do summary over those articles. So we do need a way to let the computer to somehow learn by itself, to improve by itself. So one way, a quick way. So instead of ask a human to write out a summary, what we do is simply ask the computer to write a 2 summary, and then human just say which one is better. So human, even though Humans do not want to write a summary, but they can quickly tell you which one is better. So by simply using the human judgment on which one is better, we give a reward back to the computer, the system. So using that reward, they can improve their, because the goal is to train the neural network to generate a better summary next time. So the summary generation itself is a neural network. You can think about the summary is action. The action is words. A sequence of tokens. Those are actions. The input is the state. The state is the article, original article. The output is the summarization. So this is called learning by demonstration. You teach, so you have this basic summary generation model combined with this human evaluation by comparison. Then you allow the computer to learn by itself to become better and better. So this is a very interesting result to apply reinforcement learning to text summarization. And I feel this definitely reduces the training data requirement. So this is a very quick summary on the reinforcement learning. So we touched a little bit on reinforcement learning. This is just a final result on the root measurement, which is it's like a blue score for translation. Root is for text summarization result. The higher, the better. So the extractive oracle, which oracle means it's the best, potential best. So that is, I'm just using words from the original document. But when we do abstractive summary, we actually generate new words outside of the original document. So with that, they showed that their method performs better than the classical BERT and the T5. So there's about 2% against the fine-tuned T5, but 6% against the zero-shot T5. So that is the performance improvement. And finally, I want to mention another Google research. This is from the Google speaker in our meetup, Alexandra Forst. So her team is looking at how reinforcement learning can be improved. So she demonstrated, first she showed that there are 4 ways to improve reinforcement learning. First, we can improve the algorithm. Secondly, improve the reward, how we model the reward. She actually showed the robot running, basically robot on a wheel that can, through the reward, learns to avoid the human in the hallway, right? So that's the modeling the reward. And you can also model the environment. You can change the neural network architecture, as I showed. The evolved reinforcement learning is changing the architecture, the actual architecture. So what if we can change the environment? How do we? So if the robot learns by interacting with the world, right? It gets reward from the world, but sometimes it's very hard to get many reward from the environment because it's expensive. First, the robot, you have to do simulation, because in the real world, the robot would die, would be broken. So you don't want to do that in the actual environment. Secondly, is you want to generate a lot of training data in a short time. So essentially, they propose a method called the environmental generation for zero-shot learning. And one of the applications is to design a website. So design a website. So what is a website? A website has many components, has buttons, has a box, forms for people to fill, has different components. So a typical website, she said, has on the internet, there's maybe 30,000 different kind of components. how would but a simple web page, one single page, may not have that many components. So how do we collect the data to train the neural network to design the web page? So they were able to automatically generate. So this is a more like a self-learning, a data generation. So they generate the actual page to train the network, use adversarial method. Essentially, it's more like a GAN model combined with reinforcement learning to actually generate the page. So that basically is train the reinforcement method to create a new page and then check whether that is consistent with using the maximum regret. So they are minimizing the regret. It's the same thing as a GAN model where you are minimizing the distance between the real picture with the fake picture, right? So using this kind of combination, they were able to generate a very kind of realistic website, very well designed box. So that paper was presented later presented in the end of 2021 in the Neuro IPS conference. All right, so that is my summary about